4차 산업혁명 기획 10주 2차 시강의를 시작하겠습니다. 챕터 12 신경기술입니다. 신경기술은 어떻게 사용되는가에 대해서 말씀드리겠습니다. 이 책에서 다루는 다른 모든 기술과 마찬가지로 신경기술도 연산 능력의 급속한 발전, 소형화, 고도화된 저비용 센서의 발전, 방대한 데이터에서 패턴을 분석할 수 있는 머신러닝 등을 바탕으로 발전해 왔습니다. 뇌는 화학작용에 의한 전자신호로 작동합니다. 이러한 신호들은 측정될 수 있으며 따라서 화학작용이나 전자신호를 조정하여 원하는 신호를 복제하거나 원치 않은 신호를 방지합니다. 전극 기술을 통해 단일 세포의 활동을 기록하거나 이를 작동하도록 자극을 주기도 합니다. 기능적 자기공명 기록법을 이용하면 각기 다른 상황에서 어떤 뇌의 영역이 활성화되는지 연구할 수 있습니다. 많은 연구자들이 이러한 기술적 발전을 토대로 지난 10년간 놀라운 성과를 거두었습니다. 제프리 링은 지난 2008년 원숭이가 뇌파만으로 로봇팔을 움직였던 실험을 인류 역사에서 중대한 전환점으로 평가하게 될 것이라고 주장하였습니다. 알도 파이절 연구소는 머신러닝과 시선 추적 기술을 뇌파의 대체물로 활용해서 뇌의 행동의 의도를 정확히 판단해냈습니다. 관련 동영상을 보시겠습니다.
I always felt I wanted to tackle a big question. And the big question was to understand how the brain works, maybe even to create an artificial brain. I'm Dr. Aldo Faisal. I'm the lecturer in neurotechnology at Imperial College London. I'm curious about how the brain generates behavior and what algorithms the brain uses to do that. And hopefully by understanding these algorithms, we can build technology that helps people along the way. In the 1960s, progress was mainly inhibited by two factors. We didn't have proper computers to process vast amounts of data, and we didn't have a lot of data. And that was because it was very hard to record from individual brain cells. These days, we're happy if we can achieve recording simultaneously from maybe 1,000 neurons, would be state of the art. And in 20 years' time, even if we're able to record from 10 million neurons simultaneously, that's just a fraction of the brain's total amount of neurons, or 0.01%. Virtually all of neuroscience is designed around experiments that have been exquisitely crafted to detect or distinguish between two different possibilities or two different hypotheses. But actually, our mind, our brain, our whole body did not evolve to perform laboratory experiments. Our brain and behavior evolved in the wild. In our lab, we've focused on eye movements, because actually eye movements are actions that allow us to infer very easily what your intentions are. And so we've built brain-machine interfaces that are non-invasive, that can enable paralyzed people to interact with the computer or use a robotic prosthetic arm just by the movement of their eyes. To drive home this point, we developed the Blink system, which is a simple arcade video game that you can control with the power of your eyes and our decoding algorithms. So the speed with which you can learn to operate such a system puts it far beyond existing invasive brain-machine interfaces and makes it at the same time roughly 1,000 to 10,000 times cheaper than existing technology. So over the next 5 years, we're going to see the rise of eye tracking technology, and it will become ubiquitous. Our mobile phones are going to be able to do that, our computers are already able to do that, and we're maybe going to have smart walls, houses, cars, urban environments that will track our visual attention. Being able to decode behavior from how we move our eyes will become a key technology to the success of marketing campaigns, of great interest to consumer and communication companies. But where it can be fundamentally useful and transformative is in healthcare, where if you consider that 1 in 4 people suffer from forms of neurological or mental disorders, we can actually really help people get better faster and make them more happy and productive people. These are trends that companies can actually invest in. So the hardware is not the challenge here. The challenge is, what do we do with all this data?
이러한 접근법은 두뇌 기계 인터페이스의 비용을 낮추고 사지마비 환자가 생각만으로 휠체어나 로봇식 팔다리를 움직일 수 있게 합니다. 뇌 전도 측정 장치는 뇌파를 읽고 뇌에 영향을 주는 신호를 발신할 수 있습니다. 이러한 장치들은 더 이상 실험실 장비가 아니며 웨어러블 제품으로 판매됩니다. 다른 제품들은 소리와 광선요법으로 두뇌에 간접적으로 영향을 준다고 홍보합니다. 관련하여 유망한 기술로는 집속 초음파를 통한 비침습적인 조직검사 또는 치료, 그리고 광선을 통해 뇌세포와 유전자 변형을 야기하는 광유전학 기술 등이 있습니다. 관련 동영상을 보시겠습니다. Focused 울트라사운드는 집속 초음파로서 비침습적인 조직검사 또는 치료입니다. 낮은 파워로 위치를 검증하고 환자의 반응을 얻습니다. 뇌의 해부학과 환자의 피드백을 통해서 타겟을 옮깁니다. 최종적으로 정확한 위치를 찾습니다. 마지막 단계는 강한 파워로 뇌 병변에 정확하고 지속적인 효과가 있는 치료를 합니다. 화학적 접근법으로는 뇌의 기능을 다양한 방식으로 향상시키기 위해 개발된 여러 종류의 물질과 향정신성 의약품이 있습니다. 뇌 활동을 측정하는 기술이 발전하면서 질병 치료 또는 뇌기능 향상을 위한 약물 실험에도 큰 도움이 되고 있습니다. 현재 뇌질환 치료 약물의 65%가 임상실험 3단계에서 실패하는데, 이러한 약물들을 처방하는 정신과 의사들은 약물의 효능을 확인하거나 환자 간 비교를 할 수 없습니다. 싱가포르 국립대의 신경기술연구소장은 특정 신경기술은 뇌뿐 아니라 척수와 신경 말단 치료에도 응용 가능하다고 주장합니다. 신경 조정 또는 신경 자극은 팔다리의 기능 회복뿐 아니라 주요 장기의 기능 회복에도 적용할 수 있습니다. 신경기술은 수천 년간 진화해온 감각을 넘어서는 인간도 만들어낼 수 있을지 모릅니다. 제프리 링은 인간이 적외선 시각을 가질 수 있으며 꿈의 기억을 녹화하거나 재생할 수 있고, 서로 다른 장치에서 재생되는 여러 영상들을 동시에 이해하며 팔다리와 자동화 기계를 동시에 통제할 수 있다고 주장합니다. 이러한 능력들은 생각보다 실현 가능성이 있습니다. 과학자이자 발명가인 앨런 머스크가 최근 뇌 컴퓨터 인터페이스 개발 회사에 투자하였습니다. 그는 생물학적 지능과 디지털 지능의 결합을 예견하였습니다. 관련 동영상을 보시겠습니다.
The main reason for doing this presentation is recruiting. And this will be a slow process. where we will gradually increase the issues that we solve until ultimately we can do a full brain-machine interface. Yeah, this is going to sound pretty weird, but achieve a sort of symbiosis with artificial intelligence. But I think with a high bandwidth brain-machine interface, I think we can actually go along for the ride. And we can effectively have the option of merging with AI. I think this is extremely important. Our goal is to record from and stimulate spikes in neurons and do so in a way that is orders of magnitude more than anything that's been done to date, and safe and good enough that you can, it's not like a major operation. It's sort of equivalent to sort of a LASIK type of thing. So this is in contrast to the best FDA-approved system, which is like a Parkinson's deep brain stimulation thing, which would have on the order of 10 electrodes. So the system, even in version 1 that we're going to unveil today, is capable of 1,000 times more electrodes than the best system out there, and they're all read and write. So this is really quite, I think, I mean, for something to be 1,000 times more than what is publicly approved is quite a big difference. So there's very tiny threads that are about a tenth, roughly, of the cross-sectional area of a human hair. So they're extremely tiny threads. In fact, the threads that we have, like I said, even in version 1, are about the same size as a neuron. So if you're going to go stick something in your brain, you want it to not be giant, you want it to be tiny, and to be approximately on par with the things that are already there, the neurons. You really need this to be done with a robot, because it's very tiny and it needs to be very precise. So you don't want to pierce a blood vessel. So when so each thread, the robot looks sort of basically through a microscope and inserts each electrode specifically, bypassing any vasculature, any kind of like blood vessel, and making sure that it can be inserted without causing trauma or minimal trauma. So just to give you a sense of scale, this is how tiny the threads are. That is not even a big finger, that is a small finger. So these threads are just like I said, way smaller than a hair, and there's 1,000 of them. And this is what the robot looks like. It's sort of quite a complex device, but it all comes down to a very tiny point. So we want to just like, you see the robot on the left, and then what looks like the needles for insertion next to a penny, but in fact the actual needle that gets inserted is way tinier. It's that little tiny thing at where the arrow is pointing. That's actually the size of the needle. It's about 24 microns in diameter. It's so small you can't really even see it in the picture with the penny. You can get a sense for the robot doing the electrode insertion. That's a very zoomed in view. So they're all very tiny, and the robot is very selectively applying them very delicately, and then this is what the chip looks like. So there's action potentials. So each one of those represents one electrode. So there would be up to 10,000 of these lines. The operation on a per chip basis, it involves just a 2 millimeter incision, which is dilated to 8 millimeters, and then the chip is placed through that, and then it goes back to being 2 millimeters, and you can basically glue it shut. You don't even need a stitch. And then the interface to the chip is wireless. So you have no wires poking out of your head. Very, very important. So it's basically Bluetooths to your phone. Because we'll have to watch the App Store updates for that one. Make sure we don't have a driver issue. And we hope to have this aspirationally in a human patient before the end of next year. So this is not far.
어펜딕스입니다. 브레인 컴퓨터 인터페이스의 반도체 및 시스템 기술에 대해서 동영상을 보시겠습니다. 지금까지 시청하신 것으로 이번 차수 수업이 인정됩니다.
My name is DJ Seo, and I'm the Director of Implant Systems at Neuralink. My team focuses on building chips and systems to get neural signals recorded from our electrodes out of the brain, and also to put information into the brain. Before Neuralink, I was at UC Berkeley, where I co-invented NeuralDus, which is a technology to power and communicate with small implantable systems using ultrasound waves. Typical chip lifecycle from design to verification to tape out is approximately 1 to several years. At Neuralink, we had the ability to co-design our chip with the rest of the system, and the tight feedback loop from this organization has enabled our small team of analog and digital chip designers to tape out a new design every 3 months on average. That means over the past 24 months, we've done 8 tape outs in total, representing 15 different chips that have been designed, fabricated, tested, and used in development. The artwork that you see on the top of the slide is of some of the actual chips that we've made so far. For any custom chips we make, the architecture can vary substantially, but the basic ideas are the same. Neural signals recorded from the electrode typically look like the one on the slide. And in order for us to extract the information that we care about, we need to first amplify, filter, and digitize those neural signals, and use digital logic to process and send out the bits we want for BMI. We also need ways to diagnose any issues with our electrodes and be able to drive stimulation engine to inject charge to the brain when required. Our latest chip is called N1 System on Chip, and it is physically small, measuring only 20 millimeters squared or 4 by 5 millimeters. It is low power, highly configurable, and it has 1,024 simultaneous record and stimulation capable channels. And it has on-chip spike detection. To dive deeper into N1 SoC, I'd like to highlight 3 key innovations. And they are 1, analog pixel, 2, on-chip spike detection, and 3, stimulation on every channel. The first is analog pixel. Before we can convert analog neural signals into digital bits, we need to amplify and filter them. And this is where the analog pixel comes in. We want to have 1 analog pixel per electrode so that we can configure them independently. So in the case of N1 SoC, there are 1,024 analog pixels. Analog pixels also take up a significant portion of the physical space on the chip, and how well they work determines both the signal quality and the characteristics of the overall neural interface. The goal of analog pixel design is to make it as small as possible so we can fit more, as low power as possible so we generate less heat and have longer battery run times, and as low noise as possible so we get the best signals. Now, the challenge here is that these goals are at odds with each other. For example, we want to achieve lower noise on the amplifier so that more spikes can be detected. But as transistors get smaller, it becomes harder to get lower noise while keeping the power the same or less. Since the start of Neuralink, we've gone through 3 major revisions to the analog pixel, progressively improving both the size and power while maintaining performance. Over the past 24 months, we had 7-fold improvements in the size of the analog pixel. And our latest pixel on the right is at least 5 times smaller than the known state-of-the-art of similar architecture with 1 pixel dedicated per electrode, as published in the academic literature. Second innovation is on-chip spike detection. Once the signals are amplified, they're converted and digitized to zeros and ones by our on-chip analog-to-digital converters. As you'll hear in a second, spikes or action potentials shown on this slide are often critical for certain BMI tasks. Currently, there are several different methods for detecting spikes, such as thresholding, or more sophisticated methods such as principal component analysis. At Neuralink, one of the robust ways that we came up with is by directly characterizing the shape. And it's worth noting that this is different than template matching in that it gives us more information in a general way. In certain cases, we can actually identify different neurons from the same electrode based on their shapes. Our analog pixel can capture the entire neural signals sampled at 20,000 samples per second with 10 bits of resolution, resulting in over 200 megabits per second of neural data for each 1,024 channels that we record. In our previous systems that you heard about, we were able to stream this entire broadband signals through a single USB-C connector and cable, and we performed real-time spike detection on an 8-core machine running our optimized C code. Now, we wanted to completely eliminate connectors and cables for N1, so we had to modify our algorithms to fit into the hardware by scaling both, making it both scalable and also low power. And then we were able to also implement this algorithm in our N1 SoC. Our algorithms can compress neural data by more than 200 times, and it only takes 900 nanoseconds to compute, which is faster than the time it takes for the brain to realize it happened. Finally, it was important for us to enable stimulation from every channel that we can record from and make it configurable and high resolution. To make this work, we custom designed stimulation engine for electrical stimulation that can coexist alongside our analog pixels. Our stimulation engine has 0.2 microamp of amplitude resolution and 7.8 microsecond of time resolution. There is a 16:1 ratio of electrode to stimulation engine, so we can't stimulate every channel simultaneously, but we can within each stim pulse, usually in milliseconds, and we can also stimulate any combination of 64 channels at the same time. So in summary, looking through our N1 SoC, it has 1,024 analog pixels that we can record from simultaneously with 7.2 microvolt RMS noise while only consuming 6.6 microwatt of power. It has on-chip analog to digital converters, on-chip spike detection that can compress neural data more than 200 times, and it only takes 900 nanoseconds to compute. Stimulation engine with 0.2 microamp of amplitude and 7.8 microsecond of time resolution. And finally, diagnostics for electrode and impedance measurement. All of these functionalities that I outlined are integrated into a single 4x5 millimeter silicon die.